Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mounts, and I'm glad you've taken the time to join us today as we look at our topic of the 5 key error-proofing fastening techniques. And so as we get started, when we look at error-proofing as a concept, the primary leader in this area was brought forth by Shinjo and with the Toyota management philosophy. And one of his famous quotes is, defects occur when the mistakes are allowed to reach the customer. And so if there is the possibility for us to be able to capture and fix errors before they happen, then we can present our product or our application or our assembly to the customer without any mistakes or the defects. And so this whole philosophy comes through the term you may hear poka-yoke or poka-yoke. There's a couple different pronunciations that you might hear, but this is that idea of error-proofing the actual assembly process. And we see this type of concept throughout our daily lives. And so from when you start your car, you have to have the car in either park or in neutral and your foot on the brake to go ahead and start the ignition. If you're walking into an elevator, there are sensors on the doors to make sure that the doors don't close on someone. We see it with gas pumps as well. The unit won't pump unless the nozzle is fully engaged, and then when the point of the tank gets full, then the nozzle will automatically shut off. If you try to plug a cord into an outlet, you know that there's typically only one way that goes in. And these are all error-proofing types of concepts that allow us not to be able to make a mistake. So it's kind of crafting our behavior into the outcome that we want, that is desired. And so this is not about being rigid or in that type of robot type of scenario, but we want to just be able to move in our case, when we're dealing with assemblies, move the operator in the right direction, give them the opportunities not to make a mistake, and we can then help to error-proof the assemblies a little bit better. And so again, I'm glad that you've joined us today. If you were with us last month, we were in our corporate office in San Jose. We're now in a different space, in a new space, and so there may be some things that may come up, or there may be an issue here, but nevertheless, we'll go ahead and we'll work through that. But again, thank you for joining us here today. And so, what are some of the manufacturing risks that we typically always deal with? And that is going to be around anything that needs to be reworked. If we have that type of issue, we all know that rework is expensive, and if we can help to avoid that, then these types of implementations of different components or different plans can really help to mitigate a lot of the rework that may come due to fastening types of errors. Obviously, manufacturing risks would include very safety critical type applications where we're going to need to make sure that the specification that is called for with a specific torque value is achieved. So that, again, poses some risks to us as well. And then probably the biggest risk in the manufacturing process is going to be the human error risk within the assembly process. people make mistakes. They can become distracted or not pay attention. And so this type of human element within the process does pose a big risk in the manufacturing process. Is the operator trained correctly in the position that they are doing? Do they fully understand the concept behind what is being what is trying to be achieved through a particular assembly? Does the operator have an attitude like, yeah, I really know what's best for this and I'm going to do it my way? Or have they bought into how a particular item should be done and through specific procedures? Or do they even know what those procedures are? And so, again, the human element is a big factor within the manufacturing process and the error proofing type of concept. And so causes for defects within the process as it relates to assemblies, that's going to be basically improper torque control, whether a fastener is under torqued, and that can fail due to vibration or shock, or if a fastener is over torqued, and there may be a lot of stress on the fastener, and then again, any type of shock or vibration can cause that fastener to fail. If that clamp load is too high for the particular joint characteristics. So a lot of what we see with defects around fastening is going to be the improper torque control. If a fastener was not torqued at all, if they have been missed, again, these types of scenarios can certainly play a big part in any type of error that we would see due to fastening. And so the principles behind error proofing, we touched on it a little bit when we started, but primarily we want to try to help eliminate the possibility of making a mistake, doing a preventative type of behavior that we can craft to allow the operator to do their specific operation without having to necessarily think about what it is that they are doing. What types of things can we replace or change or modify to help us, again, allow for the elimination of the mistakes? Are there certain things that we need to automate within the actual process? Are there devices or are there certain pieces of equipment that can help us do that through an automated product? Does an assembly process have the ability to detect when there is an error? If there is, then we can help to minimize that particular error, and we can correct it right away before the part moves on down the line. And then again, we have that scenario where we're dealing with rework and the expense that is associated with that. So what are the 5 keys to the fastening techniques? Well, one we've just highlighted and touched on when we were talking about the actual cause for defects, and that's going to be ensuring that we have the proper torque control. And this can be done a number of different ways. In our demonstration for today, we're going to be using our ECT DC control tool to help show those types of torque control processes throughout the actual assembly and the programming of that. But this also could be done with the use of a torque analyzer and a torque verification type of program where you are monitoring your specific tools on a periodic basis before they are sent out for calibration, because the last thing we want when a tool goes out for calibration is that tool to come back and have a as found reading that is out of tolerance. And that again can cause a number of different issues, whether that is a power tool or a hand tool. That particular tool then may be suspect to actually, when did that tool go out of calibration during the use cycle of that tool? At what point did the parts that were assembled with that, are there critical components to that? Does that need to cause the issue of doing any type of recall or notice or corrective action because of it? So if we can ensure that we're having proper torque control from the outset, this again can help in the error proofing process. And as I mentioned, you can use it in this case with a DC tool, or if you're using hand tools or electric clutch tools, if you do have that ability to monitor what is happening with those tools, that can go a long distance with the ensuring that you're getting the torque that the tools are supposed to be generating. Next key, so that was key number one. Key number two is going to be process control. This again allows us to be able to create a workflow around a specific operation or a specific assembly process. In this case, it could be a cellular type of build where there's going to be multiple different torque values and presets that may be used. And so with the process control part of that, we can help to automate certain aspects of that to help the operator move through the assembly without having to put the tool down, grab something else, and then set the tool up again or select a preset. A lot of the process control components we can handle all with the use of either digital inputs and outputs and communication. And again, it would be the use of creating an actual assembly or job around what we are actually doing in a particular assembly. So that would be key number two. Key number three is screw counting. So if we want to make sure that all of our fasteners have been torqued, we want to be able to count those fasteners to do that. And there are a number of different ways that this can be accomplished. I will show you today, again, with our DC tool on how we can integrate that into a process control scenario where we are actually counting the screws within the assembly process. There are other ways that this can be done as well. If you have an electric clutch tool that you want to use, we do have pieces of equipment that will allow you to connect to your transformer for your electric clutch tool. And that can also be used to count the number of rundowns and screws that that particular tool have done. So it will then allow you to move through the assembly. So that is the screw counting, pretty elementary, very basic. But again, if you've got a large number of fasteners and you want to make sure that all of them get done, we can certainly count those to help, again, error-proof that assembly. Next is going to be job managing. So if we do have a number of different process controls as it relates to a specific assembly, but let's say we have a mix of different items that may be presented to a particular operator, we need some way to be able to manage those jobs or assemblies. And being able to do that effectively certainly can help, again, in moving the operator to the right right setup so that they are doing the correct job without having to think about it or do any other types of settings. And then the last, our fifth key is going to be real-time monitoring. And so this allows us to be able to capture data from the fastening process in real time. We can also then get information to the operator that if there is a specific error or if there was a problem with a specific rundown, the operator is notified and then has the opportunity to reattempt that fastening to allow them to make sure that, again, everything is completed correctly. And so those are the five keys. And then we'll go ahead and we'll jump into the demonstration portion of the tool, but just want to go through those one more time if you missed those. But anyway, the first one is ensure that we have proper torque control. Number two, process control within the assembly process. Number three is our screw counting. Number four is managing our different assemblies. And fifth is our real-time monitoring. And so with that is going to bring us to our poll question for today. And that question is, do you currently have any error-proofing tools that you're currently using in your assembly process? Pretty simple today for the poll, yes, no, or not sure, maybe a maybe. I'll give you guys a few seconds here to go ahead and weigh in with your poll, and then we'll continue on with the demonstration portion of the assembly or of the demonstration. All right, so we got a few more answers coming in. And all right, we'll go ahead and end the poll now. But over half of you did answer yes with at least some form of error proofing tool. The remainder half was no and not sure. So thanks for participating in that poll. And then this will go ahead and we'll move into looking at some of the error proofing features within the ECT DC control tool that we're looking at today. And so with our first tool or our first key, we want to make sure that we have our proper torque control. And so this type of tool gives us the ability to have multiple different presets. If you're not familiar with this type of tool. So in our case, we can have up to 15 different tools, 15 different presets. And so if I log into our system here, we can then get into our menu. So we have our different menus. Today, when we're talking about our programming and presets, we're going to be in our parameter menu. Our first item is going to be the fastening tab. In here, we have the ability to go ahead and enter in what our target torque values are going to be for a specific preset. The tool that this is connected to does have a built-in sensor in it, so it is monitoring the rundown and providing us with the actual reading that the tool is producing. And so in our process here, we have our target torque. If I want to go ahead and change that, I certainly can. I can come in and I think I'll just leave it where it was, but at 2.25 Newton meters is the the unit of measurement that we're dealing with for this tool. Um, but that is how we can set the preset. You can see down on the bottom here that this is preset 1 of 15. If I want to change to a different preset, I can just tap down here. I can go to preset number 9, and now I can program preset number 9 and enter in whatever target torque we might want for that particular preset. So let's go ahead and go back to preset 1. And now we want to make sure that the result that we see from the tool will meet a specific parameter. So we can program in what our tolerance is going to be for a specific preset. So in this case, we're going to have 10%, and that can vary depending on what your requirements might be, but we can enter in that. So if we do see a reading that's outside of that, the system will generate an error, and the operator will be notified that that particular fastening was not good, and they'll need to go ahead and re-attempt that. So that gives us the ability to program the actual tolerance. The next portion within our error proofing is being able to set an angle requirement that that must be met along with the torque value. And basically what this means is, with the angle requirement, this gives us the ability to help detect fastening errors such as cross-threading or as strip fasteners. So we can set what would be a minimum amount of turn that must be met, and also a maximum amount of turn that would generate a specific error. So in our case, in our process here on preset number 1, we know that our fastener takes roughly 1,000 degrees of rotation. So we're going to set our minimum torque value here, and we'll set that to 500 degrees of rotation. This really helps to detect if there is a cross-thread event. The cross-thread is going to happen right at the very beginning of the rundown. This will obviously, the torque can be achieved, but there won't be any rotation after the threads bind up. So if the operator isn't paying attention and they do cross-thread it, it could be maybe it's a blind hole, and they would just move on because the tool did reach torque. But if we have a minimum angle threshold that must be met, if it is not, then we would get a minimum angle error. And so the next would be our maximum angle. And so we could set that at, say, 1,200 degrees. And if a fastener goes beyond 1,200 degrees in our scenario, then we would also receive an error. So these angle requirements can be used in conjunction with one another, like we have set here, or you can use just the minimum, or you can use just the maximum. It just depends, but this may be really helpful in the maximum if you're dealing with a self-tapping screw, maybe into plastics, something like that, where it would detect that the fastener has stripped once it gets past a certain degree of angle. And so that is basically how we can ensure that we have the proper torque control. The other thing that we can do is we can add an error that would generate if the operator lets go of the trigger of the tool before the system has fully completed its rundown. So you don't have a scenario where the operator doesn't complete a rundown because they let go of the trigger and they just moved on with that. So we can do that within our controller menu. We have our fastening stop error that allows us to be able to set that. So if I turn that on, this will again alert us if the driver is run without the actual completion of the torque. And so if I go ahead and run the tool now without and then let go, you can see the system generated a non-complete scenario. If I go ahead and run a fastener down, and we got our torque value, we have our angle value, which was set at basically 1,000 degrees. So we met our minimum and our maximum degree of angle. And then we also met our torque value as well. So this is how we can basically ensure that the tool is producing the torque that is needed to be generated. Again, there's a sensor that's built inside the tool that's measuring that, so we can do that. So let's move on to our key number 2 with this, and that's going to be the process control aspect. And so let me just go ahead and I can run this down again so you can actually see this. And now this may, there we go. And we'll go back to preset 1. And we'll run that down. And there we go. And so the next is going to be the process control. We did touch on it there a little bit on how we can program the different presets within the unit. But we can also then go ahead and add a fastening sequence within the actual assembly. And so this is done through the use of what we call our model mode. And this allows, again, for us to build an assembly within the actual use of the different presets that we have available. So I'm going to go ahead and zoom in a little bit right here so you can see what we have. Sorry about that. So that did not work correctly. All right, so here we can use what would be our fastening step here and another fastening. So we can call out a specific preset to be used. So in our first scenario, we would use preset number 1. And again, this is for an assembly process that would have multiple different presets within it. And we want the tool to automatically change once a certain set of tool or fasteners have been completed. And so we can call out what actual count we want for that particular preset. So it can be whatever the assembly would call for, but in our case, just to make the scenario a little bit easy for the demonstration, we'll do that. So our first one is going to be preset 1. We'll do 1 fastener. Then we'll have the system change to preset number 2. Again, we'll set it for 1 fastener. And then finally, we'll go ahead and set another fastening for preset, for preset number 3. And again, for 1 fastening. And then this one will do a no operation. And that will be our first assembly, or in this case, our first model. And when we're talking about the 4th step within our keys, that's going to be the job managing. Here we have the ability to have 15 different models that can be made up of the 15 different presets that we have available to be used. And so in this case, I'm working with model number 1 of 15, but we can also then use models 2 all the way up through 15. So that's how we can manage these specific items here within our process control. We can also use a barcode scanner that can be connected to the controller. That barcode scanner can then pick up and present a specific job, or in this case, a specific model that would be called out for that particular barcode. That could also be used with an item or part And if there are some standard identifiers within that, we could link those identifiers to a specific model. So if we come back out to our system, the one thing that we need to do within the model function is we need to put the controller into the model mode. And so right now it's in off position. I can go ahead and turn that on. And when we come back out, you'll see that our menu has changed slightly. So we're now, instead of dealing with presets, we are dealing with our model. And so we're here now, you can see model 1. We are using preset number 1. And then this is the first step within the model. And that is a fastening step within that. And so this, again, can walk the operator through the assembly. And as the tool completes a specific operation, we can then go ahead and have the unit automatically change to another preset. So let's go ahead and run this first fastener down. And now you can see that our model has changed. We're still in model 1, but now we're using preset 2. And this is the second step within there. That is a fastening step as well. And again, once we've completed that, we have moved on to our third fastening. And we have an error. This is because we have this particular fastener or this particular preset set to run a certain amount of angle. And so if I do this again, I'll just let it continue. And it will set, and our model is complete. And now it will go ahead and restart. Now it can, we can have this same model restart. We can go ahead and then lock the system and then have the operator scan the part or barcode to go ahead and release it. And then it will allow that particular model to be loaded, and then the operator can go through that particular assembly. So that gives us a lot of the features, actually 4 of the 5 here so far. We have the ensure proper torque control. We had our process control. We had the screw counting within the model function. You can see down here, our count is now at 0. And then we also had the ability to manage those particular models or assembly processes. The last one is going to be our real-time monitoring. And we saw a little bit of that here as we were notified that there was a particular error. It did allow us to go ahead and reattempt that particular fastening to see that. But if we want to also be able to send the data that is happening from the tool itself, that would be a time date stamp of the torque that was, or the preset that was used, the actual outcome of that. How long did it take to run down in milliseconds? What was the amount of angle or turn that happened? Was there an error? If there was an error, what was the error code for that one? And all of that information can be sent out of the controller, or it can be saved locally. So if again, we enter into our menu here, in our controller function, we do have the ability to select which data we want to have the unit send out. And then we also have the ability on where we want that data to be sent. So we have our auto data output. We can turn that on and we can have that automatically sent out to an MES system or another capture device. And that can be done through the RS-232 port or through the Ethernet port. And it can also be sent over Modbus or Open Protocol for this particular controller. If we don't have access to those types of systems and we still want to be able to capture the data, we can do that as well. We can send all of the data to an SD card that is on the controller as well. And so as we use the system, it will go ahead and then give us all of that data again, and monitoring what happens um, through the inputs and outputs as well. And that is done here in our IO section, where we can have different inputs come into the controller to select a preset or to disable the tool. We can also send out signals, whether it be for a pneumatic lock or a PLC device, or we want to communicate with a light tree or some other type of device as well. We do have that type of monitoring capabilities with this particular tool as well. And so that is going to bring us all the way to our question and answer. So I hope that you got some information in regards to how you might be able to craft or look at your assembly and institute some type of airproofing function to help guide your operators through the assembly process. And so with that, we'll go ahead and move to our questions and answers. So Chris, do we have any questions?
Morning, Dave. Yeah, our first question is, can you explain the difference between angle and rundown angle?
So angle is basically just the amount of turn that happens. And so in a normal circle, we have 360 degrees, or that would be one rotation. So we can monitor the amount of turn that happens with a fastener, and we can measure that from different points in the rundown. It just may depend on the particular application, but we can measure it from when the trigger is pulled. We can measure it from a spike in the torque value, or we can measure it also from when a fastener mates with the surface of the assembly. And so the only difference between those two is going to be, one would be specific to measure from a certain point, and the other one is just the definition of what angle is.
All right, Dave. The next question we have is, what is the difference between a transducerized tool and a non-transducerized tool?
So the real simple answer with that is a non-transducerized tool does not have a sensor to measure what the torque output is. Typically in the DC tool arena, there's going to be either a current control version and a transducerized version. The current control version basically takes the amount of current draw and converts that to torque. And then the transducerized system is using the actual transducer to measure the actual torque output. So that would be the difference between the two.
All right, thanks, Dave. Next question we have is, does the controller system, allow prevailing torque for like 30 threads or galvanized fasteners type of applications?
In this scenario, for our transducerized system, we do have that option where we can look at a specific value within the rundown. If there is some prevailing torque, that value can be read, and then we can add that value to the final torque that needs to be achieved, so we can get the proper clamp force or the proper stretch on the fastener. So the portion of the torque that's being basically eaten up by the prevailing torque is eliminated.
All right, thanks, Dave. Next question is, can the system be used to program for a thread tapping application?
It can as well. We can use a couple different ways to do that. We can use an actual thread tapping mode that we have. If there's a scenario where the fastener is cutting material for a portion of the rundown, and then after the cutting, that particular torque or prevailing torque is reduced below the actual seating torque, we can accomplish that. We can also use a fastening strategy that would use an angle control with a torque monitoring. So basically just the reverse of what we talked about with the preset, where we would turn the fastener to a certain degree of rotation. And then we can monitor a minimum and a maximum torque. And that could be useful in that type of scenario as well.
All right, Dave. And that looks like that's the last of our question and answers for today.
All right. Thank you very much again for joining us today. I hope you got some good information from it, and we look forward to seeing you next month with our next installment in our webinar series from Mounts. Thanks again.